as I mentioned, is on the application. Okay. Now, I would like to make use of this example, okay, in order to illustrate you the process. Okay. Now, this example is actually what I used earlier to talk about the basis of the method. And here you have three diagrams here. The one on the left-hand side is a problem that we want to solve. And it is a member of, you can consider as a vertical member of length L with rigidity EI. And the second one in the middle, this is a problem that when we want to apply them, we divide them into two elements. So you divide them into two elements. And of course, we can divide into 3 or 4 elements. But as illustration, we divide them into elements of equal length. That's why you have L over 2, L over 2. And when we divide them, we introduce artificially what we call a nodes. This is the actual end, this is the actual end. Somewhere in the center, there's actually no nodes there. But for the sake of the procedures, because we divide them into 2 elements, so now you have one node here, which is at B, okay? And corresponding in the middle, again, there are the corresponding structure loads and also structure displacement, the W and the delta, and in the corresponding positive directions. And the one on the right-hand side here, these are the element now, okay? And they are corresponding nodal forces, the Q and the nodal displacement delta in the respective positive directions. Okay. Now, this example that I'm going to show you, it has no support condition yet. This is in general, no support conditions. Of course, later we see how the support conditions are being considered. This is no support conditions, completely free, floating in the air. And later when we introduce support, this is fixed, fixed is spin. So how do we actually consider that in the solution process? Okay. Now, the basic procedure here is to form the element stiffness equations one by one. You call this element 1, you call this element 2. Okay. And in element, you need to name it, okay, so that you can go in a systematic way. Especially you need to decide which one is your starting one for element 1, which one is your ending end, element 2. So here, this starting one is here. That's why we start with Q1 or delta 1 here and until 4. And the second one, the starting one is here. That's why we start with Q5, delta 5. And then end with Q8, delta 8. Okay. So if you have one more, then you decide which is the starting one. So you start with delta 9, Q9, and then until delta 12, Q12. So it comes with 4, set of 4 here. 4 displacement and also the nodal forces. Okay. So you form the element stiffness matrix, which is this one or this one, okay, one by one. Okay. For element 1, you start with that. Element 2, you start. In this particular problem, because these are all subjected, this is a vertical member and subjected to axial force, so each of the member has P. Each of the member has P. Okay? So the P appears there. So you need to consider that. So after you get the stiffness matrix equations, then there's a part that I mentioned, which is important process, combine them. Okay? So when you combine them, we need to know what is the basis behind the combinations. we need to get the combination of the stiffness equation to the structure stiffness equation representing this problem. So in the element stiffness matrix, we have delta 1, delta Q1, Q2, the small one. When we go to structure stiffness equation, it becomes W and delta. So that process is an assemblage process, which is important, and it is a very cumbersome, lengthy process, okay, to do hand calculations. So that is a part that I want to explain to you, okay? And for that, let me go to this particular notes here, okay? This one. Now, if you, this one I will elaborate to you the basic idea behind here. These are the explanation here. This is on page, this is on page 1, I also cannot, 128, yeah, 128 on these notes after equation 2.144. This is about formation of structure stiffness matrix. And there is a two method here. Basically, they are the same, but the basic idea behind is different. They come out with the same set of equations. This is called method B, and this is transformation of coordinate. Transformation of coordinate. So this is the one that I'm going to explain to you. This part here. Let me use the whiteboard there. So the basic of getting the structure stiffness matrix from element stiffness matrix, the central concept here is transformations. Because element level, they have their own coordinate system, which is what we call the element stiffness matrix, element coordinate system. But every element must finally refer to the same global coordinate system. Then only you can combine them. You cannot combine them like you have your coordinate system like this, and the other member has this coordinate system, and another member have this coordinate system. The element stiffness equation are all defined to their element coordinate system. And in order to combine them all, you must turn them back into global first, which is common for all, then you combine. Okay? So the basis idea here to get the K matrix, yeah, I use the capital K to represent, this is a global one, but still at element level. For that particular element, it has to go through this transformation process, B transpose, the K at element level multiply with the B matrix. Okay? And because of multiply this is a very lengthy process. I think you need maybe A3 paper, 10 pages. This is a very lengthy process. And to do hand calculations, matrix multiplication, this side and this side, this is a very lengthy one. Okay? Then after we get this, then we combine. So first we have to change the element stiffness at global level. Small k is for element level. Change it into global levels first, the structure one. So after this process, everybody already at the same, referring to the same global coordinate system, which means, let's say, everybody refer now to this system and this system. At this level, one element is like this, another element like this. Cannot. So it must go through this process, and then in order to change everybody now, you refer to the global system. And this B matrix, the B matrix, let's say I call this element M, and this one is another element N, is different for each element. This B matrix, so this element has its own B matrix, and this element has its own B matrix. Okay. So this is the B matrix. The B is actually transforming the local one to global. Okay. The B matrix that we are going to look at is transforming the local to global. The global to local. Okay. Delta is the local one, and this delta is the displacement in the global level. So this B is the one responsible for transforming the global to local. The same thing because the displacement and also forces is transformed in the same way. So if you have a global forces, okay, this one I think sometimes we can use, in order to differentiate, we use the vector, and this is actually vector. Sorry. We can also use the same symbol. So this is vector, and this is a vector. So this B is actually the matrix transforming the global, everything in global coordinates to local coordinates. Okay. Now the actual process of getting this B is actually they get the directional cosine. They get the directional cosine of the local system relevant to the global system. But in our example, I'm going to show you the process of getting this directly using the example. Okay. Now, in the example that we are looking at here, we have A, B, C here. Remember our example that we use? Okay. On the other side, they cannot see. Or at the center one, there is here. This is delta 1. This is delta 2. Okay. And the mid height here, this is delta 3. This is delta 4. This is delta 5, and this is delta 6. Then at element level, I call this element 1. Okay, I use a symbol like this element. Then I have this delta 1, delta 2. And at this end here, and I have delta 3, then delta 4. And another element, which we call element 2, we start with delta 5, delta 6, delta 7, and clockwise, and delta 8. In this particular example, it is very easy because all the elements are oriented in the same directions. Okay. So in order to get the B matrix, what we do here is for element 1, you have the B matrix. Okay. B matrix for element 1. So you look at how to relate the global to local. Okay. So delta 1, you look at for element 1 is actually at the same nodes here is equal to delta 1. And then delta 2 equal to delta 2. Then the other end, delta 3 equal to delta 3, delta 4 equal to delta 4. This for this example. Okay. Then the B matrix, when you want to get to the B matrix, the information that we need is delta 5 equal to delta 5 equal to delta 5 is corresponding to this n here. Yeah? Okay. Delta 5 is equal to delta 3. Delta 6 equal to delta 4. Yeah, this n of the element number 2 is actually coincide with this. Then delta 7 is actually equal to delta 5, and then delta 8 equal to delta 6. So now the B matrix will be, if I put it delta 1, delta 2, delta 3, delta 4, I put it in matrix form now, is relating to delta 1, delta 2, delta 3, delta 4. This is the B matrix. So in this case, it is just the identity matrix. This example is because all the members is oriented in the same direction and coincide with the global x-axis, so it becomes like this. Then for element 2, we have delta 5, delta 6, delta 7, delta 8 equal to the matrix, which is B2, multiplied with delta 3, delta 4, delta 5, delta 6. And this one again is identity. Later, when I meet you again, when we look at other examples, it's not identity anymore. This one is the process of getting. So the idea here is if you go to any problem, to get B, you need to relate the local nodal coordinates, local nodal displacement to the corresponding global one. So once we get this and this, then we make use of this into these equations. Then first we get the element stiffness equations, element stiffness matrix for element 1 in global, in the global coordinates. Then repeat, go to element 2, do the same thing like this, transpose this first, then multiply with K, and then multiply back with B, then we get for element 2. Then after you get this, you can combine them. Okay. So, but when you combine them, then how do we combine them? Then you have to refer back to this, and this one now. Okay. The process of combinations. Yeah? The process of combinations. Okay. Put it back here. So when you do combinations, you rely on this to combine. So for element 1 at the global level. So when you change it into already multiplied with B transpose small k and B, so you get your matrix. Yeah, you get your matrix, which is already changed it to refer to the global system. Then you pay attention to what is the global one here. Okay. And for the element 2, also you pay attention to the relation to the global one. Delta 3, delta 4, delta 5, delta 6. And these are element stiffness matrix at global level. You need to combine them. So when you combine them, you are guided by this delta 1, delta 2, delta 3, delta 4 to decide where you put them inside the structure stiffness matrix. That is the process of combining element stiffness matrix into global one. So when you want to combine these two, combine them, yeah? So what we do for combination is you decide where to put each of these element stiffness matrix into the structure level one. Okay. So this is at the structure level one. There is no 1 and 2 anymore. This is structure level. And the structure level will be the size of the structure corresponding to how many global degrees of freedom that you have. So it has delta 1, delta 2, delta 3, delta 4, delta 5, delta 6. This is what you have now at the structure stiffness matrix level. Then you look at this, delta 1, delta 2, delta 3, delta 4. So this, for this element 1, I should put inside here. So this is also corresponding row number 1, row number 2, row number 3, row number 4. This is row number 5, row number 6. Okay. So here, whatever is here, which is 4 row, 4 column, comes into here. So this is assemble. And finish with element 1 and go to element 2. So whatever is here, this is also 4 row, 4 column, go inside there. So go inside there means it has to come here. Okay. So you start feeling that, okay? And then you have overlap here. Overlap means whatever is here, then you have to add them up. When you have overlap means you have to add them up to form the overlap part there. And the remaining part, which is doesn't fill up by any element, it will be 0, 0. This will become 0, 0, 0, 0. This one 0, 0, 0, 0. Okay. So this is assemble process. Okay. So it is a very tedious process to do it manually. Okay. But you need to understand this. This is how computer program is doing. So computer program will tell them, we already tell them the relationship. Then they follow these rules. Okay. So computer program can easily assemble 4 by 4, 10 by 10, 6 by 6. But for us to assemble, this is ideal. Get the global first, and then this one corresponding to which row, which column you should put inside, you put inside there. So that is the structure stiffness matrix. Now, for this problem that we want to solve, as I mentioned, there's no boundary conditions. Later, when you have boundary conditions, then you start to take away column, delete this, delete that. This is how we consider boundary condition. This is no boundary condition yet. So if you cannot solve this, when you try to solve something without boundary condition, you get determinant 0. You get the cases where you cannot solve it, I think, because this is unstable. Okay. So you must have to consider the boundary conditions. So later, when you want to consider boundary conditions, meaning that this is fixed, if this is if The bottom part is fixed, the top part is fixed. That means something happened to the delta 1, delta 2, delta 5, delta 6. When it is fixed, delta 1, delta 2, 0. Delta 5, delta 6, 0. Then we start to delete. We start to take away the column. So this one becomes smaller. Reduce it. Okay. So this is how we solve. Then finally, after we consider boundary conditions, now if we want to solve for P critical, then we use the non-trivial condition. The determinant of the K must be 0. Then we get equations. It can be quadratic equation, it can be cubic equation. Then we solve equation, get the smallest one that gives us the P critical. Okay. So class, that is the process of getting the structure stiffness matrix. Form the B first, which is the transformation for each of the element. Then calculate the K, the element stiffness equations, which already transform to global stiffness, a global coordinate system. Then after that, decide where you put inside. Here, the big one. This is called assembly. Okay. If you have overlap like this, mean whatever you come from this part must be add up with this part here. Okay. So this also means that the two element is connected. Then, when the two element connected, then you have overlapping. Okay. And this means that this element has nothing to do with 5 and 6, because element has nothing to do with 5 and 6. Element 2 has nothing to do with 1 and 2. Okay. That's why they are 0, 0, 0, 0 there. When you have overlapping, means the element is connected there. Okay. So that's the assembly process. And when you come back, I meet you again next week, we'll look at the boundary condition part and then how to apply the non-trivial condition to get the determinant. Okay. Any questions, class? So I will stop here for today.